Now we derive the relation among the Einstein's coefficients A21, B12, and B21. We consider the system at thermal equilibrium. The per unit volume absorption rate is given by this equation. The downward transition rate per unit volume has two contributions. One is the stimulated emission. The other is spontaneous emission. At thermal equilibrium, there is no net optical transition imbalance. Therefore, the total upward transition rate must equal the total downward transition rate. And this equation must hold. Substituting the three expressions gives this equation as shown. Now we use the equilibrium occupation vectors. Since the system is at thermal equilibrium, the two levels share the same Fermi level. So we have EF1 equals EF2. From the Fermi Dirac distribution, one obtains the equation shown here. Also, for black body radiation, the photon spectral density must be equal to the photon density of states at energy E21 times the average photon occupation number per mode. Using these two equilibrium relations, we obtain this equation from which the following two relations can be derived. So we have B12 equals B21, and A21 over B21 equals the photon density of states at energy E21, which can be further rewritten as shown in this expression as we have already derived previously. In fact, there is no surprise to see that B12 equals B21 because for a Hermitian interaction Hamiltonian, we know that H sub 1 to prime minus must be equal to the complex conjugate of H sub 2 1 prime plus. So their squared magnitudes are equal. And regarding the second relation, this result has an important physical meaning. Stimulated emission and spontaneous emission are not unrelated processes. The spontaneous emission coefficient A21 is connected to the stimulated emission coefficient B21 through the density of available photon modes, capital N of E21. In other words, spontaneous emission depends on the number of electromagnetic modes into which the photon can be emitted. Here we ask one important question. Under what condition does stimulated emission dominate over spontaneous emission? To answer this question, we take the ratio of the per unit volume stimulated emission rate to the per unit volume spontaneous emission rate and use the Einstein relation A21 equals B21 times the density of states for photons at energy E21. We obtain this result. This result is very simple and very important. The ratio of stimulated emission to spontaneous emission is equal to the average photon occupation number per mode. If there are very few photons in the resonant optical mode, spontaneous emission dominates. If there are many photons in the mode, stimulated emission can dominate. This explains why an optical cavity is so important for lasers. A cavity provides feedback. It allows photons to remain in the active region or system longer, thereby increasing their lifetime and allowing stimulated emission to build up the photon occupation in selected modes. As the photon number in the cavity mode increases, stimulated emission becomes much stronger. The figure on the slide shows standing electromagnetic waves inside an optical cavity. The forward and backward traveling waves interfere constructively, forming standing wave modes. Only wavelengths satisfying the resonance condition described by this equation can be strongly supported by the cavity. Here capital L is the cavity length and M is the longitudinal mode number. This equation suggests that as long as the cavity length can accommodate an integer multiple of a half wavelength, standing wave patterns can be established within the cavity. Notice that in a laser cavity, the photon energy distribution is generally not a thermal Bose-Einstein distribution. The photon occupation number of a lasing mode at a specific photon energy can become very large because of optical gain and feedback. Therefore, the first conclusion is that to make stimulated emission far exceed spontaneous emission, we need a large photon concentration in the relevant optical mode. An optical cavity helps achieve this by increasing photon feedback and selecting resonant modes. On this slide, we want to compare stimulated emission with absorption. The ratio of the per unit volume stimulated emission rate to the per unit volume absorption rate is shown in this expression. Using the Einstein relation B12 equals B21, the B coefficients cancel. The photon spectral density, capital S of E21, also cancels. Therefore, we have the result as shown. For stimulated emission to exceed absorption, we need the ratio to be larger than 1. This condition simplifies to F2 must be larger than F1. This is the condition for population inversion in a two-level system. It means that the occupation probability of the upper level must be larger than that of the lower level. This is a very important conclusion. A larger photon concentration helps stimulated emission dominate over spontaneous emission. But to make stimulated emission dominate over absorption, we need population inversion. In other words, a laser requires both conditions: a large photon population in the optical cavity and an inverted medium in which the upper transition level is more populated than the lower transition level. When we later move from a two-level system to a semiconductor, this condition will become a condition on carrier distribution in the conduction and valence bands. For a direct interband transition, the corresponding condition is that the occupation of the conduction band state must exceed that of the valence band state for the same transition energy. Therefore, we typically require FCK must be larger than FVK, meaning the occupation probabilities of states in the conduction band exceeds that in the valence band at the same K point in vertical transition. This is the origin of optical gain in semiconductors. As we will see later, under quasi-equilibrium, this requires the separation between the electron and hole quasi-Fermi levels to be larger than the energy band gap.